Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 3.4, the chain rule.
Lesson 2, more challenging examples. So, I'd like you to look at this one. You're asked to find the derivative of x cubed sine of 5x minus 1. And what you might want to do is what we did in the last example. Think about what the overall rule that you're going to apply to this is by thinking about the overall structure of what kind of function you have. So pause the video, give it a try, and why don't you go ahead and decide what the overall rule is, and maybe also think ahead to any other rule that might come into doing this problem, and then restart the video. We'll talk about what rule to use, and then I'll let you go ahead and give the whole problem a try yourself. Well, when I look at this particular example, I see that I have one function, x cubed, times a second function, sine of 5x minus 1. So the overall structure of the function I'm asked to differentiate is really a product in this case, and it's a product of the function f of x equals x cubed times the function g of x equals sine of 5x minus 1. Now that means that the overall rule that I'm going to use is the product rule. Is there any other rule that I'm going to need along the way when I find the derivatives using the product rule? Well, remember that the product rule is going to be the first function times the derivative of the second plus the second function times the derivative of the first. That's the pattern that I'm going to use. And when I take the derivative of this second function, I'm going to be taking the derivative of sine of 5x minus 1. Notice again, this is not a product. It's not sine of x times the function 5x minus 1. It's sine of 5x minus 1. 5x minus 1 is inside the sine function. So there's an inner and an outer function in this function that we're calling g. And that means that we will need the chain rule in order to find that derivative. So what I'd like you to do is go ahead and go back to the product rule and think of doing your f times g prime plus your g times f prime. But when you do this g prime, the derivative of the second, write it using this operator notation and don't actually take the derivative until the following step. And that way we'll split the problem apart into two steps and we won't be trying to do two different differentiation rules in a single step. So give that a try and then pause the tape again or restart the tape again and we'll go through it together. Okay, so let's try this together. We're going to just apply the product rule for the time being. We know that later on we're going to need the chain rule, but I'm going to try to leave that for a second step. The product rule, if I think of x cubed as my f and sine of 5x minus 1 as my g, I'm supposed to do my original first function, so that's x cubed, times the derivative of my second function, but that's where we said we're going to run into complications because this second function that I'm calling g is actually the composition of two functions. There's an inner and an outer. I know I'm going to need the chain rule for that, and that looks more complicated to find the derivative of, so that's what I'm going to leave for the next step. So I'm just going to go ahead and use my operator notation and say it's going to be the first function times the derivative of the second, but I won't do the derivative of the second until the next step simply because it looks fairly complicated. So this is my f times, I'm not doing this derivative yet, but it's times the derivative of my second function. And now, according to the product rule, I have a plus sign, so here's where my plus sign goes. And I'm supposed to do the second function, which is this thing, my g is sine of 5x minus 1 times the derivative of the first function. So I could write again with my operator notation d by dx of x cubed, but this one's so easy to differentiate because I just use the power rule that I'd probably just go ahead and find f prime. F prime would be the derivative of x cubed, which would be 3x squared. So overall we have f times g prime, we haven't figured that out yet, but times the derivative of g plus g, the second function, times f prime, the derivative of the first function. And now we're done with the product rule. But we're still not done differentiating. And why aren't we done differentiating? Because we still have this derivative left to do. And as we said before, because there's an inner function, namely 5x minus 1, inside an outer function, sine, and it's a composition of two functions, what rule do I need there to find that derivative? There I will need the chain rule. So if you haven't already done this part of the problem, go ahead and pause the tape, give that part a try, and don't forget to carry everything else down, and then simplify your answer as much as you can. Restart the video and we'll go ahead and do these details together. Okay, let's go ahead and try to do this together then. This part of the problem is already done, so I'm going to pull down the x cubed. It's going to be times the derivative of this. That's the only derivative I have left to do. And here, this 3x squared, because it's a polynomial, we would usually switch the order of these two factors. So I'd write it as 3x squared times sine of 5x minus 1. That's to make it really clear that the only thing that's inside the sine function is the 5x minus 1, not the 3x squared. That multiplies sine of 5x minus 1. Okay, so let's look at this one. I'm supposed to do the chain rule on this, and that means that I have to redecide what my f and g are using the chain rule. Let me do that in a different color. So forget about what we called f and g before. We labeled them specifically for the product rule. Now I'm using the chain rule, so I'm going to have a new f and a new g. My outer function is going to be sine of whatever I plug in, and my inner function, g of x, is going to be 5x minus 1. So in a little cloud over here, if you want to, you can remember that now the outer function for this derivative that we have left to do is sine of x, or in general, f of whatever I plug in is sine of whatever I plug in. So according to the chain rule, I'm supposed to do the derivative of the outer evaluated at the inner, and then I'm supposed to multiply by derivative of the inner function. So let's go ahead and see if we can do that together. I start by doing the derivative of my outer function. Well, my outer function is sine x, so derivative of the outer, derivative of sine, is cosine. And so I would normally write down cosine x, but we'll just write cosine of whatever I decide to plug in. Well, what am I supposed to plug in? According to the chain rule, I'm supposed to plug in my inner function. So it's derivative of the outer evaluated at the original inner function. So I put a 5x minus 1 inside my cosine function. And then I'm supposed to multiply by derivative of that inner function. Derivative of 5x minus 1 is 5. Okay, now we've done all the derivatives. We used the product rule as our overall rule. When we were doing the derivative of a portion of that, however, we also needed the chain rule, and we did that in a separate step. The rest of the problem is just algebra, just cleaning it up. This 5 I would pull to the front and make it 5x cubed times cosine of 5x minus 1. And then I have a plus 3x squared times sine of 5x minus 1. And we would probably just leave it that way. You could pull out a common factor of x squared, but generally we won't factor these answers at the end. We'll just leave them this way. Okay, well, let's go ahead and look at one last example. I want us to do it together because it's a rather complicated one. And It's again an example where we have to use more than one rule. The reason I want to do this one, even though it's kind of hairy in terms of the algebra that we will need, is precisely because of that. A lot of the exercises in your textbook will require you to do some manipulation in terms of algebra. And this is a typical example of the kind of messy algebraic problem that you'll come up with in many of the homework problems for this section and future sections. So I thought it would be good to go through that together and just tackle one that's a messy one together. So here I'm asked to find the derivative of 4x squared minus 5. All of that is to the third. Then the whole thing is divided by 2x cubed plus 1. All of that is raised to the fifth. So you can see that this is a pretty messy problem. Well, let's go ahead and see if we can decide what the overall rule we need to use to differentiate this is. And remember, that means we want to look at the overall structure of the function we're asked to differentiate and ask what's the main thing that's happening. And when I look at this, the main thing I see happening is that I have one function in the top, namely 4x squared minus 5 to the third. So I have this function in the top, and I'm just circling it in red because my red pen is a little bit lighter than my purple pen. And I have this other function in the denominator, 2x cubed plus 1 to the fifth. I'm going to call that g. So the main thing I see happening is I have an f divided by a g. I have something divided by something. That means the main thing that I have happening is a quotient of two functions. So in order to find the derivative, what rule do I need? I'm going to need the quotient rule. And that's going to be my overall function, my overall rule, I should say, of differentiation. That's the overall thing I'm going to need. However, remember that when we use the quotient rule, we're going to be taking derivative of the top, derivative of the bottom. And when I take the derivative of either the top or the bottom, can you see what additional rule I'm also going to need? Maybe I'll just put it in parentheses here. Later on down the line, I will also need, well, to take the derivative of the top, I can see it's a composition. There's an inner function, 4x squared minus 5, all raised to the third power. So I will need the chain rule to find the derivative of the top. And in the bottom, I will also need the chain rule. I have an inner function, 2x cubed plus 1, all raised to the fifth power. So somewhere along the way, I will also need the chain rule. And in fact, I'll need it more than once, because when I take derivative of the top, which will come up somewhere in the quotient rule, and when I take the derivative of the bottom, which will come up somewhere in the quotient rule, I'm going to need the chain rule. Again, we'll try to separate things so that we use only one rule at a time, and we're going to start with our overall rule, the quotient rule. Well, remember that we call the top function f and the bottom function g. If you want to, you can think of it as f being the higher function, the high function, and g being the lower function, which we usually write just as LO, the low function. And we could use our jingle to remember the quotient rule, or you can simply remember g times f prime minus f times g prime divided by g squared. It's fine if you've learned it that way. I'm going to use the jingle just because it's a little bit easier for me to remember. So remember, the jingle has to rhyme. So I have to do low, d high. I'm going to give myself a lot of room. Minus high, d low. And then square the low, and away we go. And if it doesn't rhyme, it means I've got these terms in the wrong order. So that's the nice thing about the jingle. Okay, well, let's go ahead and see if we can write that out for this function. I'm supposed to do my original low function, which is this whole thing. It's 2x cubed plus 1 to the fifth times the derivative of my high function. But when I take the derivative of the higher function, because there's an inner and an outer function, it's a composition, and that's where I would need the chain rule. That looks really complicated for this higher function. So instead of actually doing the derivative in this step, I'm simply going to use my operator notation and say times d by dx, in other words, times the derivative of 4x squared minus 5 cubed. So what I have so far, the low d high, it's the original lower function times the derivative of the higher function, but I'm waiting until the next step to actually do that derivative because I can see it's going to involve the chain rule. Now I bring down my minus sign in my little pattern here, and I'm supposed to do the original higher function. Okay, so that's this, 4x squared minus 5 to the third, times the derivative of the lower function. But again, that looks complicated. I can see I'm going to need the chain rule. So instead of doing it in this step, let's just write times the derivative of times d by dx of 2x cubed plus 1 all raised to the fifth. And that way I'm not trying to do both the quotient rule and the chain rule in the same step. It's just so hard in something that's messy like this that it's much better to just take one extra step. And you'll get pretty fast at doing that one extra step as you go. Okay, so that's the numerator of the quotient rule. The denominator is supposed to be the lower function squared. So I just want to take my original lower function, which is 2x cubed plus 1 to the fifth, and square that. Great. Well, we've written out the quotient rule, and now we're all done with the quotient rule. Anything that I've labeled as f and g, forget about it, because we're done with using the quotient rule where we were thinking of our overall function as some f divided by some g, and we'll relabel things in terms of new functions f and new functions g to find these remaining derivatives that I have left to do. So let me go ahead and do those remaining derivatives. And let's look at this one right here. We said that in order to find that derivative, I am going to need the chain rule. So I'll just put chain here. To remind myself I need the chain rule for that. And we said to do this one, because it's also a composite function that I'm trying to find the derivative of, I will also need the chain rule. Let's pull down everything else that we're done with. Notice we're done with this portion, so I can go ahead and pull that down, 2x cubed plus 1 to the fifth power. And now I want to use the chain rule on this. Well, that means I have to decide what my inner function is and what my outer function is. And the inner function is just what's inside the parentheses. So my g of x for the chain rule, I'm doing it in a different color so I don't get it mixed up with the g that I had up here. My g of x for the chain rule is just 4x squared minus 5. That's my inner function, and my outer function I can see is the cubing function. It would really be f is equal to x cubed. So using the chain rule on this portion, what do? I go ahead and take the derivative of the outer. That means I'm going to be pulling down the 3 and doing whatever I'm plugging into the second power. So that's derivative of the outer, and I have to evaluate it at this inner function. So I'm evaluating it at 4x squared minus 5. So that's the f prime of g of x factor in the chain rule. But remember, there's another factor in the chain rule. I have to take derivative of the outer, evaluate it at the inner, and multiply that by derivative of the inner. So I have to multiply that by g prime. What I have done so far, let me go ahead and just kind of put a bracket here so we can see that all of this is using that chain rule. What I've done so far is to do derivative of the outer, evaluate it at the inner. Now I have to remember to multiply by derivative of that green inner function. And what is the derivative of 4x squared minus 5? That would just be 8x. So all of this stuff is using the chain rule on this portion that we still had left to find the derivative of, so this circled portion here. Okay, great. Well, now let's go ahead and go to the next term over here. This part was already done, the 4x squared minus 5 to the third power, but I still had to do this derivative, and we said we would need the chain rule again for that. I have an inner function, and now my inner function, my g, will be 2x cubed plus 1, and I have an outer function that would really be f of x would be x to the 5th power. So we have to use the chain rule again. Let me go ahead and write down the pattern for our chain rule right above it. It's going to be derivative of the outer evaluated at the inner times derivative of the inner function. And so what goes right here is going to be the derivative of this expression that I have circled in green above. Okay? Derivative of the outer. That means I want to pull down my 5 and raise everything that's left to the 4th power. So that would be the derivative of this outer function, the x to the 5th function. Derivative of x to the 5th is the 5x to the 4th. Where do I want to evaluate that, though? We want to evaluate it at the original inner function. So derivative of the outer evaluated at the inner, and my inner function now is 2x cubed plus 1. So derivative of the outer evaluated at the inner, but by the chain rule I must multiply by derivative of my inner function. Derivative of 2x cubed plus 1 would be 6x squared. And now I think I'm done with all of my derivatives. I'm going to carry down what I have here. Why don't I simplify it a little bit? I notice I have a base, 2x cubed plus 1, raised to the 5th, and then that whole thing is raised to the 2nd. It's really a power to a power. What do I do with the exponents in that case? You might remember that you multiply the exponents. So I would end up with 2x cubed plus 1 raised to the 5 times 2 would be to the 10th power. Well, let me go ahead and kind of neaten up this first term that's in the numerator and this second term that's in the numerator, and then I'm going to show you the kind of hairy algebra that we can use to simplify even further. You might be tempted to want to multiply everything out in the numerator and combine like terms, but that would be a very difficult way to simplify this expression. So I'm going to show you an easier way to use your algebra skills to simplify it. Well, let me put the smaller factors to the front. I have a 3 times 8x, so I'm going to put a 24x here. And then I'm going to write down my 2x cubed plus 1 to the 5th power. That's the next factor I see here. And I also see a factor of 4x squared minus 5 to the 2nd. So that's just cleaning up this first term that appears in the numerator. Now I want to subtract off, well, if I look at the shorter factors, I have a 5 times 6x squared. That would be 30x squared. And the next thing I see here is the 4x squared minus 5 cubed. I'm actually going to write this factor first so that I have those bases in the same order that they were in this first term. So I'm going to pick up this factor next. That's the 2x cubed plus 1 raised to the 4th power. And then I have a 4x squared minus 5 raised to the 3rd power, and the whole thing is divided by 2x cubed plus 1 to the 10th. Well, that looks like a pretty messy expression, but we certainly wouldn't want to start multiplying all this out. You'd have to multiply 2x cubed plus 1 by itself 5 times, that binomial, and so on. It would be almost impossible to do the problem and not make any errors by multiplying everything out and then trying to combine like terms. A much better way to simplify this is to simply try to find the greatest common factor in the numerator. So let's go ahead and look at the first term and the second term and see what factors they have in common, and we'll try to pull that common factor out of those terms. So let's see if we can remember how to do this from algebra, and this is a particularly messy one, that's why I chose it. I'm going to look at the numbers first, 24 and 30. Greatest common factor of those, the biggest number that divides evenly into both of those, would be a 6. So when I look at the 24 and the 30, I can pull out a common factor of 6. When I look at the x and the x squared, Well, the only thing that's common to both of those is x to the first power. You could think of that as x to the 1. We have to take it to the lowest power we see it, because this means x times x, this means x. The only thing that's common to both of them is a single factor of x. So I can pull an x out of those two. And in a similar way, we can think about the common factor between this thing, 2x cubed plus 1 to the 5th, and here's 2x cubed plus 1 to the 4th. There are only 4 factors of that in this term, so the most I can pull out is 4 factors. That's all this term has. So the greatest common factor is going to be 2x cubed plus 1 to the 4th. There just isn't a 5th factor of 2x cubed plus 1 for this term. So that's the most I can pull out of both terms. And then if I look at this last factor, 4x squared minus 5 to the 2nd and 4x squared minus 5 to the 3rd, again, there are 2 factors of 4x squared minus 5 here, 3 factors here. The most that are common to both, that both of these terms have, is the 2 factors. I have to take it to the lower power. So the 4x squared minus 5, the best I can do for the common factor is to pull that out to the 2nd power. And then I will be left with a bunch of stuff over here. So we're pulling this factor out of this term, and we'll get something left over, minus, and then we'll pull it out of this term. We'll get something left over, and the somethings that go inside these purple square brackets have to be exactly the right thing, that if I distributed this back out and did this times this, I would get this first term, and did this times this, I would get this second term in the line above. And of course this whole thing is divided by 2x cubed plus 1 to the 10th. Well, let's see what's left inside these purple brackets. I'm pulling a 6x out of a 24x. That means I would be left with a 4. I'm pulling a 2x cubed plus 1 to the 4th out of 5 copies of that factor, 2x cubed plus 1 to the 5th. So if I pull 4 of those factors out, I'll be left with just 1 factor inside here. So I'll be left with a 2x cubed plus 1, really to the 1st power. I'm pulling out a 4x squared minus 5 to the 2nd, and that means that I'm pulling this whole thing out. And notice that if I were to distribute and multiply this green junk by this purple junk, I would get the first term in the numerator on the previous line. Okay, let's go to our second term and see what's left when I pull these factors out of the second term. If I pull a 6 out of a 30, I will be left with a 5. If I pull an x out of an x squared, I'll be left with an x. If I look at the 2x cubed plus 1 to the 4th, well, that's this entire factor here, so I'm pulling that whole factor out, so I'm not left with any of it left in here. And when I go to 4x squared minus 5 to the 2nd, well, this is 4x squared minus 5 to the 3rd, so I do have one additional factor of 4x squared minus 5 here. You could think of it as 4x squared minus 5 to the 1st. When you multiply these two together, we would get 4x squared minus 5 to the 3rd. So now we've pulled out the greatest common factor. Why don't I also simplify what's inside these purple brackets just to make it a little bit easier, and I'm going to do that in red. Inside these purple brackets, if I distribute out, it looks like I have an 8x cubed plus a 4 when I distribute the 4 to each of these terms. When I distribute a minus 5x to each of these terms, I'll have a minus 20x cubed. Negative 5x times negative 5 would actually give me a positive 25. And that's really the terms that are inside these square brackets. Okay, well, let's go ahead and go to the next step then and see if we can start to simplify some things. Oh, before we leave this step though, notice there is now a common factor in the top and the bottom of the overall expression here that I could cancel. What's like in the top and the bottom, I have a 2x cubed plus 1 to the 4th in the numerator, and that does multiply everything else in the numerator now. So I'm allowed to cancel that with like factors of 2x cubed plus 1 in the bottom. I have 4 copies of this factor in the top. It's 2x cubed plus 1 times itself 4 times. And I have 10 copies in the bottom. So I would be left with 6 copies in the bottom if I canceled 4 of these. So imagine writing this out 4 times, writing this out 10 times. You could cancel 4 of the factors in the top and the bottom. You'd be left with just 6 of them in the bottom, and it'd be gone completely from the top. Okay, now I think we're ready to write our final answer. I still have a factor of 6x. This factor is gone. I have a factor of 4x squared minus 5 to the second. And now I'm going to write what's left in these purple square brackets. I'm going to turn them into ordinary parentheses though. So let's just write those with rounded parentheses, but they're taking the place of these square brackets. And if you look at what we have written in red, we can combine some like terms. I had an 8x cubed minus a 20x cubed. Well, that gives me a negative 12x cubed. And what else do I have? I made an error. You probably caught it. When I was multiplying this out, I did negative 5x times negative 5. What should this have been? It should be a positive 25 because it's negative times negative, but I forgot the x. Let's stick that in. So it should have been a 25x, my error. So I have 8x cubed minus 20x cubed gives me the negative 12x cubed. And then if I'm going to put it in descending form, the next thing would be a positive 25x and then a plus 4. And so I can't simplify what's inside these parentheses any further. There are no more like terms to combine, and it doesn't look like that's going to factor into anything that might cancel with the denominator. So I'll leave that in that form. And all of this is divided by what's left in the denominator, which is 2x cubed plus 1 raised to the 6th power. And I believe that is as simple as we can make our answer, and so that would be our final answer. Well, wow. Phew. That was difficult. It was really only difficult, I think, because of the algebra and pulling out the greatest common factor in a complicated expression like this. But it's good practice because this type of algebraic manipulation, this type of simplifying, will come up a lot in chapter 3, where we start to work with all kinds of crazy functions and their derivatives in applied situations. So it does come up quite often, and that's why I wanted us to do one that was really complicated together. And of course it was also complicated because we needed 2 different rules to find the derivative. We needed our old quotient rule, and we needed our new rule, the chain rule. Okay, let's go ahead and look at the next example. Well, on the next page, I just want us to look at a couple of examples that contain the composition not of 2 functions, like all the ones that we saw earlier, but the composition of 3 functions. And let's see if that is indeed what I have in this first example. I'm asked to find the derivative of sine of cosine of x cubed. And you notice that it isn't a product of 3 functions. It is not sine x times cosine x times x cubed. That would require the product rule to find the derivative. But that's not what I have here. I actually have 3 functions that are composed. The very innermost function is x cubed. And notice that is inside of the cosine function. So if you just looked at what's right here, cosine of x cubed, that all by itself would be the composition of 2 functions. If I were asked to find the derivative of that, I would need the chain rule. But that is actually inside a 3rd function, namely the sine function. So the cosine of x cubed is inside the sine function. Well, how the heck do we find the derivative when I've got 3 functions stacked up? And the easiest way is to go ahead and work from the outside inwards. So I'm going to go ahead and say, well, I'm thinking of my outer function for the time being as sine of x. So over in my little cloud over here, we would be thinking, oh, f of x is equal to sine x, meaning f of empty parentheses is equal to sine of empty parentheses. So that's kind of what I'm thinking of in my first little thinking cloud here. And what's inside of here, well, it happens to be a composition of two functions, but for the time being, let's just say, oh, well, the thing that's inside this, the outer function, the outermost function, is cosine of x cubed. So I'm going to call that whole thing my g of x. So g of x is going to be this whole thing cosine of x cubed. So we work from the very outermost function first. We think of that as our f, and whatever is inside of that, that whole thing is our g when we apply the chain rule. So I'm going to go ahead and apply the chain rule here and work from the outside in. Okay, well, what did the chain rule say? It said find the derivative of the outer, evaluate it at whatever your inner function is, and then multiply by the derivative of that inner function. Okay, so we just start like we normally do with any chain rule problem, and we take the derivative of the outer function. So I'm going to be taking the derivative of sine, or you can do it up here in your mind if you want to. Derivative of the outer function, derivative of sine x is cosine x. So derivative of sine of empty parentheses is cosine of empty parentheses. So derivative of my outer function is cosine, and I'm supposed to evaluate that at my original inner function. So let's go ahead and put in our original inner function. That's whatever g of x is. And remember, g of x is this whole thing. It's cosine of x cubed. So what have I done so far? I've done derivative of the outer evaluated at the original inner function at g of x. That's only the first factor in the chain rule. Let's write down the second factor in the chain rule. Well, the second factor is the derivative of my inner function. It's g prime of x. However, when I look at this inner function, it looks pretty hard to find the derivative of that. In fact, if I were to ask you just to find the derivative of cosine of x cubed and forget about the sign that's on the outside for a moment, remember that it itself is a composition of two functions, so what rule am I going to have to use to find its derivative? I would actually need the chain rule again. Okay, so that's too hard to do all in one step. We've done the derivative of the outer, evaluated at the inner. I'm supposed to multiply by the derivative of this inner function, but because it looks tough, I'm going to go ahead and use our trick of waiting until the next step. And how do I wait till the next step? I simply use my derivative operator notation and say, oh, it's going to be times the derivative of the inner function. And I'll wait to do that derivative until the next step. That way I won't get all confused, because actually in this problem I've used the chain rule once, but what am I going to have to do to find this derivative? I'm going to have to use the chain rule a second time. So I will need the chain rule a second time here to find the derivative of the inner function, because it happens to be a composition of two functions as well. Okay, so let's see how the heck we do this. Well, this part's all done. It's cosine of, and the inner function just also happens to be cosine of x cubed. We're done with that part. Now I just have to find the derivative of the inner function, and that is a new function that I'm asked to find the derivative of. So forget about all of this stuff and just imagine I gave you this problem and said find the derivative. You would have to label a new f and a new g and use the chain rule again. So totally forget about the f and g we had up here. That was for our first application of the chain rule. Now I decide again what my f and g are. So we're just looking at this portion of the problem and we're saying, well, what's the outer function? The outer function now is cosine, and what's inside the cosine function, that's going to be my g of x, that's x cubed. So if I were to do another little thinking cloud over here, my outer function, f of whatever, would be cosine of whatever, and that works fine if I call my inner function g of x, x cubed. So as we go through the chain rule this second time, remember to use our green designation for what f and g are, and forget about our original red designation of what f and g are. So now we're just concentrating on this portion of the problem, and I go ahead and say, okay, I'm using the chain rule. So I'm going to use my little pattern, derivative of the outer, evaluated at the inner, times derivative of the inner function. Well, what's the outer function now? Now the outer function is cosine. Derivative of cosine is a minus sine. So I'm going to have minus sine. And remember, we're supposed to evaluate that at the original inner function. What's my inner function? That's x cubed. Let me write that in a different color so we can see it. So the inner function is x cubed. So we've done the first factor in our second application of the chain rule. Derivative of the outer, that's minus sine, evaluated at the inner, x cubed. But don't forget, the chain rule requires us to then multiply by the derivative of whatever our inner function is. And our inner function g is just x cubed. So I'm just taking the derivative of this inner function, and that one luckily is easy to do. Derivative of x cubed is a 3x squared. And usually we don't like to put a times and a minus sign right next to each other, so for that reason oftentimes people will put an extra set of parentheses here, because it's going to be all of this stuff times derivative of the outer, negative sine, evaluated at the inner, x cubed, times the derivative of its inner function. Derivative of its inner function would be 3x squared. And now we've done all of our derivatives, but notice we had to use the chain rule not once, but twice when we composed three functions together. You might think about, what if I had four functions stacked up? A function within a function within a function within a fourth function. How many times do you think you would need the chain rule in that case? You would actually need it 3 times. So if I have the composition of 2 functions, I need the chain rule once. If I have the composition of 3 functions, I need the chain rule twice. And if I had the composition of 4 functions, I would need the chain rule 3 times. Always one fewer times than the number of functions that are composed together. So it can get fairly complicated, but it's part of the reason that this is referred to as the chain rule, because you sort of get a chain of derivatives kind of going here, and they're all multiplied together, and that's part of the reason that we call the chain rule the chain rule. Well, let's just clean this up a little bit, because I would like it to look a little bit nicer than this. I have a 3x squared, and you could think of there being a factor of -1 here. Let me pull those short factors out to the front. So I would write this as minus 3x squared. Then I would probably write this shorter factor next. So I'd write times sine of x cubed. And then I would write this longer factor here. It's cosine of x cubed. And all I've really done is to rearrange the order of this factor, which is multiplied by this factor, which is multiplied by this factor. And that's how I would write my final answer. Okay, well, the last thing I'd like us to do on this page is to look at this other example. And what we'd like to do is to go ahead and think about it in the same way. You notice it looks kind of complicated because I have e, and it's not just raised to the secant x, it's raised to the secant 3x. And don't forget that this is that shorthand notation that we use for trig functions. Anytime you're asked to find the derivative of something that involves this shorthand notation, always rewrite it in the longhand notation. And what do we really mean by that? So I'm going to leave the derivative symbol alone. We're not taking a derivative, we are simply rewriting what we're asked to differentiate in a form that's easier to think about. So I'm going to write it as e raised to, and this thing that is in the exponent, secant cubed x, really means secant of x, that whole thing raised to the 3rd power. So this would be e raised to the secant x, and all of that is raised to the 3rd power. So this is what's in the exponent of my e function, my e to the x function. All right, I want you to pause the video and then try to work this out think about how many functions are composed here maybe, and how many times you are going to need the chain rule in order to do this problem. And then try to do it the way that we did. And remember, the way that we did it was we worked from the outside in. So we started by thinking, what's my very outermost function? And then whatever's inside it becomes the g of x in the chain rule. So this is a tricky one. If you get stuck, just restart the video and we'll go through it together. Okay, let's go ahead and think about this, and I'm going to try to use the same colors that I did on the last one. I really do have three functions composed here, because you notice that I have an innermost function, secant x. That's inside the cubing function, the x cubed function, and all of that is inside the e to the x function. So I do have a composition of three functions. And that means I will need the chain rule how many times? I will need it twice, always one fewer than the number of functions that are stacked up or composed together. Well, remember last time what we said was you start with your f being the very outermost function, and we sort of work from the outside in. So my outermost function is actually going to be the e to the x function. So if I put a little cloud over here for what my outermost function is, f of x would be e to the x, or f of empty parentheses would be e to the empty parentheses. Well, if that's my outer function, I have to ask what's the inner function, and the inner function is whatever is inside these parentheses here, and that would be this whole thing. So all of this is going to be my g of x. So g of x would be secant x, that whole thing cubed. So I'll just write underneath here that g of x is actually going to be secant x cubed. That is what's inside the e to the x function. And I can see that if I did f of g of x, I would get e to the g of x, and that would be e to the secant x cubed. Okay, let's go ahead and use the chain rule then. And remember that when we use the chain rule this first time, we are working from the outside in, so I'm going to go ahead and write down my pattern. It's derivative of the outer, evaluated at the inner, and then times derivative of the inner. So let's see if we can do that. I start by doing the derivative of the outer function. Well, what is the outer function? The outer function is the e to the x function. Derivative of e to the x is its own derivative. It's e to the x. So when I take the derivative of this outer function, I actually get the same function back again. I get e to the whatever. So e to the x is peculiar that way. Maybe I should make my arrow come down here. When I do derivative of the outer, I get the same function back again. That's derivative of the outer. I have to evaluate that at my inner function. So the thing that goes in here is my g of x. And what is g of x? It's this whole thing. It's secant of x, that quantity cubed. All right. So far, we've applied the chain rule, and we said it's derivative of the outer, evaluated at the inner, and now I have to multiply by derivative of my inner function. So I have to multiply by g prime, but g prime looks difficult because g of x itself is a composition of two functions. It's secant x inside the cubing function. I don't want to do the chain rule again in the same step, so I'm just going to use my operator notation and say, great, that's fine, but I don't want to do that step yet because the derivative of the inner function looks complicated. So I'm simply going to write times the derivative of my inner function, and I make use of my operator symbol and just say it's derivative of the outer, evaluated at the inner, times derivative of the inner, and I'm going to wait to do that to the very last step. Okay, this part we are done with. So I have e raised to the secant of x cubed. I took away one of the set of parentheses there, don't really need those. And now I have to do derivative of secant x cubed. So kind of ignore all of this stuff that we did before And let's go ahead and concentrate on just doing this last derivative. What rule do I need to do that last derivative? Well, we have an inner function and an outer function. It's a composition. I have to use the chain rule again. So I use the chain rule a second time here, and that means I have to think again about what my outer function is and what my inner function is. So forget our old designations for f and g. They no longer apply. My inner function is now secant x, so that's going to be my g of x. And what's my outer function? Well, my outer function is really x cubed. If I want to write it with empty parentheses, I could say it's f of whatever I throw in is whatever I throw in to the third power. So that's what I'm thinking in my head. Well, let's go ahead and write down the pattern. I'm going to write it underneath because I didn't leave myself much room here. So I'm going to write, I need the derivative of the outer evaluated at the inner times the derivative of the inner function. And forget all of this part of it just for a moment, and we'll just concentrate on doing this last remaining derivative. Okay, here's my outer function. It's the cubing function. So when I take derivative of the outer, well, what do I get there? I'm going to end up pulling down the 3, that's derivative of the outer, and then all of that stuff will be to the second power. That's derivative of the outer. I have to evaluate that at the inner function. And what's my inner function? My inner function is secant x. So I put a little secant x in here. So that's the first part of the chain rule, derivative of the outer evaluated at the inner. Now I have to multiply by derivative of the inner. Well, derivative of secant x, remember what derivative of secant x is? It actually has two factors in it. It's secant x tangent x. So this is the derivative of secant x. That's the derivative of my inner function. The rest of the problem is just cleaning things up. I really have this factor, e to the secant x cubed, times all of this other stuff. Let's bring the shorter factors to the front. You notice I have a 3, and I have a secant x squared times another secant x. That's really secant of x to the third power. I could write secant x in parentheses and raise it all to the third, or I can use the shorthand notation, and we usually go back to that at the end of the problem once we've done all our derivatives. So it would be 3 times secant cubed x, then there's a single factor of tangent x, and you could write that factor first if you want to, that would be fine, either way. And then I still have this factor, it's e, and I could write it as secant of x to the third, but let's again go back to our shorthand trig notation. I'm going to write it as e raised to the secant 3x, so secant cubed of x. And this is the way that I would write my final answer. Oops, see if I can write that in a way that we can still see it. So it's 3 secant cubed x times tangent x times e to the secant, and that's a 3. I'll write it with a black pen so that you can actually see those exponents. This is a 3, and this is a 3. 3 secant cubed x times tangent x times e to the secant cubed x. And that's how we would usually write our final answer. Okay, well, the last thing that we're going to do in this section is kind of to give you a little bit of an idea of why the chain rule is true. You might remember that at the beginning of this section, when I introduced the chain rule, I told you that it's quite difficult to prove, but that I would try to give you an intuitive argument for why the chain rule is true. And in giving you that intuitive argument in the next couple of pages, you are also going to learn an alternate notation for the chain rule that is sometimes helpful in some application problems.